Hello, and welcome to this technical webinar from the editors of Tech Briefs Media, SOSA and its impact on OpenVPX. I'm Lisa Rico, your moderator for the next 60 minutes. Today, we'll hear from three experts. They are Mark Littlefield, Vertical Product Manager of Defense at Kontron America; Roger Hosking, Vice President and co-founder of Pentek; and Ken Grob, Director of Embedded Computing Architectures at Elma Electronic. After their presentations, we will have an audience Q&A. If you have questions, please submit them at any time through the Ask a Question box on your screen. Next to the Ask a Question box are resource links where you may download PDFs of the speaker's slides, as well as technical papers from the sponsors of today's webinar: Atrion, Elma Electronic, Kontron America, Meritech, and Pentek. And now it's my pleasure to introduce our first speaker, Mark Littlefield, the Defense Vertical Product Manager at Kontron America. Mark is an embedded computing industry veteran with more than 25 years of experience, ranging from software and systems development, program and product management, and business unit leadership. His responsibilities include managing defense-specific products, supporting business development and sales through system architecture and technical solution analysis, and participation in various industry standards activities. Mark previously was a computer vision research engineer at NASA. Mark, thanks for being with us today.
Well, thank you very much for having us, and thank you everyone for joining us today. So today I'm going to talk to you a little bit. I'm going to give you a brief introduction to SOSA, just so that you kind of know a little bit about what the organization is trying to do. I'm going to move into the slot and module profiles that have either been developed by the SOSA group or have been adopted by the SOSA group. And then I'll jump into the meat of my presentation, which is how those profiles map to standard products that you'd find within the VPX market. And then I'll wrap up with a few slides on kind of the impacts that the work that we've done is already having on the market. So I will start with a slide that I blatantly stole from the Navy, but it's such a great slide I couldn't help but share it. Hosted was a Navy activity that sort of predates SOSA a little bit, but it's been kind of rolled into the SOSA activities, but it really shows what we're trying to do. If you've got a platform like an aircraft or a ground vehicle or something like that, it might be fielded for 25 or 35 years, 45 years even or more. You got to expect system upgrades periodically. And those system upgrades have traditionally been very expensive. You take the entire system out, you put a whole new system in. And it takes time. With an upgrade like that just simply doesn't allow the integrators to kind of keep up with the march of technology. And so the idea is that we want to be able to enable periodic component level upgrades of a system so that we can quickly do technology refreshes and basically put the best technologies into the hands of the warfighter. So if you take a look at the SOSA website, you'll see this chart that basically captures a charter, if you will, of SOSA. And I'll just mention that the whole idea is to create this open architecture that standardizes certain mechanical and electrical and software components to make it easier to build these kinds of systems. As far as how SOSA is organized, we have some basic working groups, which are the architecture, hardware, software, electromechanical, and business working groups. And they're creating the actual content that's going into the standard. But then there's certain subgroups and task teams and standing committees that are working on specific kind of laser-focused problems within the standard. Use cases, security, issues around low latency. Radar has its own working task team because it's such a tricky domain to work in. Sensor management, system management, conformance, and then finally community and market outreach. But to summarize all of that, there's really three basic goals of the SOSA standard. One is to reduce the complexity and to simplify system integration, using basic building blocks to enable integrators to choose the best, most affordable solution for their application. And basically, what we want to do is to reach that dream that the integrators always want, that they can have a reasonable expectation that different modules, perhaps from different vendors, will just work when they put them into the system. And likewise, when they take a module out of an existing system to upgrade it with a new module with new technology, that again, there's a reasonable expectation that it'll just work, or at the very least reduce the integration time and cost. I also, in mentioning that, the technology insertions is a big part to be able to enable those technology insertions, make it easy to insert new technologies, being able to replace modules rather than the entire system. And then finally, to break vendor lock. It's very easy right now for a vendor to get locked into a system because everybody's got their own implementations of things. Well, this whole effort is really designed to help break that. So let's go into the slot module profiles in SOSA. So in the past, and OpenVPX is a good example of this. If you take a look at the standard, there is a lot of profiles in there. And all of the profiles have some number of user-defined pins, sometimes a lot of user-defined pins. So you've got vendor-specific pin assignments on different kinds of boards. That gives you backplane incompatibility with previous hardware generations, and certainly with hardware from different vendors. And there's really no rules for board-to-board connectivity. So you know, it's kind of, I use the term Wild West sometimes in the way that VPX is done today. What SOSA is trying to do for the future is to minimize the number of common slot profiles, and that those profiles have no user-defined pins. And I've got a little star there because there's two exceptions, and I'll talk about that in a moment. There's primary and secondary profiles that are defined, and the idea is that integrators should be using the primary profiles unless there's a good reason to use one of the secondaries. And you'll see again why there's primaries and secondaries, and why those secondaries are important to the market and to the infrastructure. And then lastly is some clear guidelines about backplane implementations, about how to design systems to maximize ease of integration and ease of technology insertions. So if we take a look at the 3U slot profiles, 3U is a little tight because there's just not a lot of pins to play with. And so we've got a few more profiles in 3U than 6U. Basically, we have two primary profiles. You'll see them at the top here. That's the what's called the IO-intensive slot profile and the compute-intensive IO slot profile. And then there's two other primary profiles, the switch profile and the I/O profile, which that's the exception that has the user-defined pins, and I'll talk about that, why that exists in a later slide. And then there's two secondary slot profiles, a secondary switch and a secondary compute-intensive profile. Now, what I don't have here is there's a profile for radio clocks. But I won't talk about that because that's a pretty specialized kind of board. These are more general kinds of boards that you'll see out in the marketplace. In 6U, it's a little simpler because we have more pins to play with. There's simply a primary 6U slot profile or payload profile, if you will, and then there's a primary switch profile, along with a secondary payload profile, and again, that specialized I/O profile. And again, there's a radio clock profile that I'm not going to talk about here. Now, as far as module profiles go, we do have some support for current what you might call legacy profiles that include like PCI Express on the data plane. But we're really encouraging that the data planes for this current generation and probably for the next generation as well of products be based on 40 gig Ethernet for fat pipes or 10 gigabit Ethernet for ultra thin pipes for the data plane. With the control plane, it would be 10 gig Ethernet. The expansion planes are a little more complicated because there's different use cases involved. One would be PCI Express Gen 3. That would be for connecting SBCs to peripheral devices of various kinds. Aurora for FPGA to FPGA links, and then low voltage differential signaling for very specialized low latency signaling to again, specialized devices. And then with all of these, there's common rules for port depopulation. And so, there's certain kinds of boards that basically wouldn't use certain ports or would use a reduced version of a certain port. And so there's very definite rules about how those depopulations work. So jumping to how those things that I just summarized, those profiles that I just summarized, map into the product space. The working groups have spent a fair amount of time looking at this and thinking, what makes sense? What kinds of products do we use? How do those products map to these slots? How would vendors create new products around these profiles? So if we start at the top, single board computers are the easy one, because the slot profiles were designed for single board computers. You notice no user-defined pins. Everything is defined. That means everything is locked down. You can't have vendor specialization with regards to the interface. You're allowed to innovate on the board all you want, but when it comes to how it talks to the rest of the system, that gets locked down. So like I said, the SBCs are pretty basic. You've got a rich selection of I/O. Often you're a carrier for XMCs or other kinds of mezzanines, and so there's mappings for XMCs to the backplane. Oftentimes you'll have like host to peripheral connectivity that you'll have to deal with. And basically those are really addressed well with these two primary profiles. However, there's the need on the market for more specialized SBCs or like, specialized I/O modules like RF receivers and things like that. So we've got profiles that were designed specifically for the needs of those kinds of boards, things where you've got a high-performance SBC or an FPGA where you need fat pipes to be able to feed the processor or to feed the results on to the rest of the system. And so if you look at the 6U profile, the 6U primary profile, and then the primary and secondary 3U I/O intensive profiles, you'll see these fat expansion pipes, much bigger than the ones that are found on the compute intensive. And that's to support those higher bandwidths. You sacrifice the standard I/O, things like USB and serial ports and video, for those bigger pipes, and likewise you sacrifice XMC mappings again to maximize for bigger pipes. It's really also ideal for like FPGA to FPGA communication because we've defined Aurora as one of the protocols that's allowed to be applied over the expansion plane. You can do high bandwidth FPGA to FPGA communication over the expansion planes. And then if you take a look at applications like GPU applications, you need to be able to talk to a GPU with a very fat PCI Express link, and these slot profiles provide that from the host side. Now, lastly, these profiles also have apertures for fiber optic and RF connectivity. So if you're doing something like an RF receiver or specialized radio or something that requires a fiber optic link, you've got the aperture there. And those apertures, I won't go into the details here, but we've also defined what fills those apertures. And there's only so many types of things that can be filled in those apertures for that sort of connectivity. So let's take a look at another type of board that's common in this space, and that's a graphics processor. You'll see them in 3U and in 6U. And these profiles are really ideal for those. You've got those fat pipes of expansion plane, which would be the primary way that you would connect a graphics processor to a host processor. Generally, that's a pretty tight link. Generally, these boards aren't standalone, so that wide, either 8 or 16 lane PCI Express connectivity is really crucial. In these kinds of boards, typically they won't have Ethernet or maintenance ports, and so those ports would be unused in these kinds of products. Another common product is a storage product. Network attached storage or peripheral storage is really common. For NAS, you would generally use a control plane or a data plane link, either in full or perhaps depopulated, depending on the application. That allows the NAS then to be, to be addressed from any node in the network. And because those are usually intelligent devices, they've got a CPU, the maintenance port can be really useful at that point. The peripheral storage, on the other hand, typically will use PCI Express for something like NVMe. That would make it a little more tightly linked to the host SBC. And again, in that case, maybe the maintenance ports and the control plane ports would be unused because you probably wouldn't have intelligence on those kinds of products. Now, I mentioned a couple of times the I/O boards. These are almost entirely user-defined, but these aren't a get-out-of-jail-free card. What these are intended to is to talk to either very specialized I/O, like perhaps legacy aircraft discretes or things like that, or some sort of specialized I/O that's specialized for that particular platform. And the rules that are written into the standard say that you can use this to address those kind of non-standard interfaces, but that you're not allowed to use this again as kind of a get-out-of-jail-free card. But you notice that there's expansion plane ports as well as control plane ports, and those would be the primary paths to talk to these boards from the rest of the system. The expectation is that boards like this would be generally program-specific. So I'm going to wrap up by talking a little bit about what the impacts we're already seeing on the market by SOSA. And reality is we're already seeing the impacts. Contron, we're already shipping 2 3 USBCs that are aligned with the standard, even though the standard is in work. Most of the important things that come down to building SBCs are nailed down. And so we're actually shipping, and we've got multiple customers out there that are working with our systems today. We've got more 3U and 6U boards actually in the works, so you're going to see more from us. There's several more vendors that have announced SOSA-aligned SBCs and other products, I should mention, in addition to SBCs. And I'm certain there are plenty more out there that are in the works that just haven't been announced yet. Plus, there's SOSA-aligned backplanes and various systems that are at various levels of testing today. So just briefly talking about the 2 products that we offer today. The first is the VX305H 40G board. It's an SBC based on the compute-intensive, or what's sometimes called the payload slot profile. Very straightforward. It's a Xeon D-based processor. It does have an XMC, but the XMC doesn't map to the backplane, so it's intended for things like attached storage or specialized front panel I/O or something like that. And again, aligned with the SOSA technical standard. And then its companion product, the VX305C-40G, is the very, very similar board, same architecture, but with the I/O-intensive slot profile. And so it brings out all of those standard I/Os of like USB and SATA and video and the XMC mappings and such. Both of these products also offer VITA 46.11 system management. And again, both are shipping today. And with that, I will pass it on to Roger.
Oh, well, thank you, Mark. That was a great presentation. Yes, our next speaker is going to be Roger Hosking, the Vice President and co-founder of Pentek, where he is responsible for new product definition, technology development, and strategic alliances. Roger has spent 3 decades in the electronics industry and has written hundreds of articles about software, radio, and digital signal processing. He also holds patents in frequency synthesis and spectrum analysis techniques. Prior to his current position, Roger served as engineering manager at WaveTech Rockland. Roger, thanks for joining us today. I see you've brought with you a poll question for our webinar audience. Let's bring that poll question up on screen now. It is, after adoption of SOSA, how soon do you expect to be building SOSA architecture systems? Please choose either sooner than 2 years, between 2 and 3 years, later than 3 years, or no definite dates. Please make your selection and then submit your answer. We'll review the results later in the program. And now, Roger Hosking.
Thank you very much, Lisa, and thanks everybody for joining today. Pentek, you may be aware of, we've been delivering high-performance RF, A to D, D to A converter, and FPGA products, which are extremely centric to the sensor architecture systems that are out there. And of course, SOSA is one that we are extremely interested in. Pentek is a member of the community outreach group, and also we have a member on the hardware working group as well. So we're very aligned with SOSA rather, and we're also shipping SOSA aligned products. So let's talk a little bit about what I would like to cover today with that kind of background. We're going to be looking very quickly at the DoD MOSA initiative, what the main objectives were, and then take a look at some of the new technologies that we are developing that can drive opportunities in the SOSA arena. And then how do the present OpenVPX architectures satisfy some problems, but yet not all of them, and how it's evolving through some of the new standards and the new things that really SOSA is very responsible for initiating changes to cause the OpenVPX to evolve. And finally, we'll cover some classified discussion technology, how that's handled, and then a final summary. But first, I'd just like to review the 5 major DoD objectives of the modular open system architecture, which are already been laid out quite a bit by Mark in his previous presentation. Better competition, technology refresh, innovation, cost avoidance, savings, and then interoperability. These are kind of the goals, the golden rules, if you want, of what the open system architecture is. So once that was released by DoD as saying this is how you shall go forward, each of the 3 U.S. military services took it upon themselves to develop their own standards in alignment with the MOSA objective. The U.S. Navy developed the HOST, Hardware Open Systems technology. The Army, CMOS, that was their initiative, which incorporated standards that they liked, like OpenVPX and Vita49 and more, and Victory. And then the Air Force, the Open Mission Systems, developed their own version, their own view of open system architecture, and incorporated some other standards as well, including OpenVPX. And what's happened recently within the last several years, that each of those 3 groups have then converged in their efforts to create a single standard that is called SOSA. And this then will take the best of each of those individual initiatives to create the SOSA objective and the standard when it finally is developed and released. So what are some of the drivers? What are some of the problems that SOSA is trying to address? And one example is a new very high performance chip called the Xilinx RF SoC chip that has 4 gigahertz 12-bit A to D converters, and there's 8 channels and 8 channels of very high-speed D to A converters, 100 gigabit Ethernet interfaces, memory peripherals. This type of product is extremely interesting because it addresses a lot of the sensor interfaces that you need to build things like, let's say, a radar that's mounted in some military vehicle like this. Boards are available that have this chip on it in 3U VPX, OpenVPX, and which are ideal candidates for then systems that can bring that technology into a SOSA-aligned system. And the challenge is then you have to deal with all of these very high-speed signals. You have to maintain signal integrity. You have to have synchronization. You have extremely high data between the boards and between systems. And you basically need to support the infrastructure that will then allow these boards to work up to their performance levels that are needed for the system. So some of the ways that OpenVPX has helped, of course, is to, in the original spec, it created a tremendous vendor base with a lot of capabilities that are ideal for SOSA, and that's why so many of these tri-service initiatives adopted OpenVPX. But what's happened is, in trying to extend the OpenVPX to cover some of these newer opportunities, VITA 65.0 and 1 evolved in 2017 to be a little bit more organized and address some of these new applications like very wideband signals, analog I/O, high length, high speed data channels, synchronization, timestamping, and so forth. And this then is what is making the OpenVPX standard evolve. Let's take a look at some of the things that are extremely important for these wideband RF systems. For example, this is a view of the backplane that is very attractive to SOSA, and you can see the 3U VPX connectors here. The second one from the left is a full 3U VPX, but you'll see that some of those sections of the VPX connectors have been removed in the other slots in the P2 area. Sometimes it's half of the P2 connector, sometimes it's the full P2 connector. And for example, in these apertures, you can install RF or optical connections. You see a multi-channel optical RF insert that is installed in that open P2 slot over to the right. But you also can have half P2 connections. For example, like this one, that is a P2B connection that provides, for example, an optical connection to the backplane. Looking at these a little bit more specifically, on the optical side, this is VITA 66.4, which is really extremely good for for digital RF signals. What you'll see is a ferrule, which is an empty ferrule floating inside of a aluminum housing that's on the module here. That then mates with a ferrule that's mounted inside of a housing on the backplane, which is shown at the bottom. The nice thing about this, we're currently getting up to 28 gigabaud on each of the lanes in those optical ferrules, so that we can handle up to 12 gigabytes per second on each 100 gigabit Ethernet interface. But these lanes also support any optical protocol. And it's really necessary to haul the data from board to board, from slot to slot, and between systems using these high-speed optical links, because it's one of the best ways to do this job if you have very, very high data rates. Taking a look at the RF coaxial backplane, just a little bit more detail, we have systems now, signals now that are up to 40 gigahertz in many requirements that can be handled with some new standards in the VITA 67, which is primarily the RF coaxial backplane I/O standard in the OpenVPX. So here you see a 4-slot, 4-channel coaxial connection. There are a lot of different types. This uses half of P2, as you can see on the backplane and on the module, but you could also occupy the whole P2 connection, replace it with a larger insert that goes into an aperture on the backplane to support 8 or 12 coax connections, as you can see here. So even in the SOSA group, there are some new objectives that will allow you to mix between the optical and the RF. Here you see half and half. And there are several new defined types of these VITA 67 that have various combinations and counts of optical and RF connections. Another very important thing for these high-performance systems is synchronization across sensor channels. As you probably know, many of these systems are phased array systems where you have multiple A to D converters or multiple D to A converters that must have synchronous sampling across all of the channels. And if this is not done, then the whole concept of the beam steering that's performed by these phased arrays just falls apart. This is very difficult to achieve, and so part of what some of the new VITA 65 radio clock distribution initiative is to create a specification that will take you from a clock driver module that's in one of the VPX slots and deliver across equal length lines that are matched in length from slot of the clock driver to each of the individual receiving slots, so that the clock signals arrive at precisely the same time on each of those destination clocks. This then can provide the synchronous operation that you really need, and it also supports time stamping. Very helpful in achieving these kinds of performance levels. Also, the original VPX power supply allowed for a lot of different voltages for the primary power as well as for the auxiliary power. The trouble is that any given power supply would often be mismatched to the requirements of the boards, because you'd be delivering high current on one of those three, and you might need more current on another one of those three. So one of the SOSA initiatives is to cut those down to two: a primary high current 12-volt supply and a auxiliary 3.3 volt supply to handle the main power for the system, and then the auxiliary power for the platform management requirements in the system. This can greatly simplify the chassis, the backplane, power supplies, and also aid in all of the objectives that SOSA has enumerated. The other initiative that's being borrowed from the VITA group, of course, is the platform management or hardware management, intelligent platform management. It goes by several names. What this does is it allows a system controller to manage all of the different resources that are plugged into the VPX backplane, to check on their health, to see who's there, to configure those interfaces, to maintain control of the software revision levels, to do a hardware reset, to maybe recycle a boot up of a particular module that is in need of that, and then also to collect all the information about that system. So this is, again, something that's very important and will be probably adopted exactly from the existing 4811 standards. There are several different types of transactions that go on across the backplane between boards. One is the message interconnection space, and the other is wideband low latency. In the message interconnects, these are relatively low speed informational transfers that take place for supervisory reasons between boards to control them and monitor their performance. But because a lot of these systems require extremely high data rate streams, often digitized signal streams from A to D converters or D to A converters, either point-to-point or multicast, these are very high data rates, and they also need to be delivered with often deterministic delays and very low latency. In addition to these data streams, you also have information or metadata that must accompany those streams to identify the source, how, where, when it was acquired, and then what do you do with the data in terms of your signal processing at perhaps the destination that receives those streams. Fortunately, the VITA 49.2 VITA Radio Transport Initiative satisfies a lot of these requirements and has already been adopted by MORA and OMS that have been then pulled into the SOSA and into the SOSA group as well. Here we're presenting the fact that because VITA is an open worldwide membership, and a lot of the things that need to be discussed in the SOSA group could be classified information, and SOSA is restricted to U.S. citizens. So what can happen is the SOSA group can explore some of these more sensitive or classified technologies, pass along sanitized recommendations to the VITA standards without divulging any sensitive information, so that those can then be incorporated in OpenVPX and then used and adopted by the SOSA group. And this last slide is kind of a summary of how everybody works together. The OpenVPX gives you a lot of standards. Those standards are down selected to a few profiles. Those then can be refined and adopted in certain ways by SOSA. The ones that are acceptable are simply then incorporated within SOSA. The ones that have deficiencies can be fed back to the Vita65 group to update it, modify it, add new profiles and so forth as required. Those new revisions become part of the Vita65, and then the new modified profiles can be adopted within the SOSA specification. As time goes on, those new requirements will drive some new needs, and then that loop repeats where the new needs are identified, modifications are requested, and new profiles are adopted. So it's a very symbiotic relationship, and we see it working quite well. It's still underway. SOSA is not fully done, but we're very excited about it, and we're putting resources at Pentek, people and product development efforts to support it. So that's the end of my presentation. Thank you.
Oh, thank you, Roger. That was excellent. Thank you. It's time now to bring up on screen the results of the poll question we asked earlier. The question was, after adoption of SOSA, how soon do you expect to be building SOSA architecture systems? And the most popular answer was sooner than 2 years, with no definite dates coming in as the second most popular answer. Roger, what do you think of these results?
Well, it's heartening to see the less than 2 years, because that is relatively a short cycle. It means that customers are talking to vendors and asking for SOSA-type solutions. And so I think once it is adopted, it will become very popular, and there will be kind of a race to get products out as quickly as possible. So that's a very positive answer.
Thanks, Roger. And now, please join me in welcoming our final speaker, Ken Grob, Director of Embedded Computing Architectures at Elma Electronic. Ken is responsible for driving the company's integrated solutions. He is a veteran of the embedded computing open architectures industry and an active contributor to the developing SOSA standards. Previously, he worked at IBM and later became the co-owner of an embedded subsystems integration company. Ken, thanks for joining us today.
Thank you, Lisa. Nice to be able to address the topic today of SOSA's impact upon OpenVPX. And as Roger and Mark have already addressed some of the impacts of MOSA and SOSA, I'll try to be brief on that topic. So, by way of some background, packaging standards have been driven largely by Vita and PICMIG around the Eurocard form factor for decades. And recently, as Roger and Mark pointed out, DoD introduced an initiative called Modular Open Systems Approach, or MOSA, to address future needs. And these largely are to improve systems capabilities, compatibility, and cost. And this effort is actually influenced by numerous other standards that you've probably seen at least some of. So if we look at those, as Roger pointed out, the various service branches, Army, Air Force, and Navy, had separate initiatives in development that have aggregated underneath SOSA. For instance, the Army has CMOS, C4ISR, EW Modular Open Suite of Standards, and the Navy had HOST, Hardware Open Systems Technologies, and the Air Force began with Sensor Open Systems Architecture. So these various standards have been consolidated underneath SOSA, and again, best of breed being folded into it, where each one of them still gains what they need from their individual efforts, and SOSA is sort of leading the charge. I might mention that SOSA is a consortium. It's administered by the Open Group. So we all belong, those of us who participate, to this consortium. And what SOSA has done they have picked OpenVPX as sort of the hardware standard for the hardware implementation to leverage what's been done in prior work, and also because this OpenVPX technology makes sense for them to adopt. So if we look at some of the SOSA objectives, collaboration between government and industry. This is a way that this collaboration can take place in this open environment. And this is good, it's healthy, get to talk about what the government needs, at the same time what the industry has to offer and where the current technology is, and work on developing better ways to get things done. So some of the primary objectives: specify base system architectures for common systems, select a hardware standard, which is OpenVPX, promote interoperability through more constrained slot and module profiles, as Mark was alluding to in his presentation. Use system management, which has been around, but now is being sort of mandated to be used in the architecture through VITA 46.11. And as Roger discussed, normalizing the power interface at the power module. And then support, which hasn't been discussed yet, higher power modules through new cooling techniques. Elm is interested in these things because we're a packaging company producing electronic packaging, chassis and backplanes, and we also provide integrated systems as well. So some OpenVPX profile basics. It can be confusing when you look at OpenVPX for the first time with the hierarchy of profiles that OpenVPX is comprised around. When you look at it, and if we just touch on the past standards, VME and Compact PCI or PIC-MG standards, at that time, a VME bus backplane, there were some variations to it, but it was a bus, and you had a VME slot, and you could plug a VME card into a VME slot, and a large part of that bus was standardized, so you could have interoperability. Similar to Compact PCI, it was fairly well defined, and it was relatively easy to make a standardized Compact PCI board that could be plugged into a Compact PCI backplane. In the case of VPX, it's a little tougher. VPX is, some folks, you'd look at it as like a recipe or a cookbook where you had various module profiles, slot profiles rather, that you would take and build a backplane from to build the infrastructure for a system. So interoperability was a bigger issue with OpenVPX. So in OpenVPX, we have the notion of a slot profile, which defines where pins go in that slot, and protocols that are assigned to that slot that are done by the module profile. And a group of those slot profiles are arranged to form a backplane profile, which captures a system topology. So these are some basic concepts of the OpenVPX profile definition. This is a collage of profiles that are now aligned with SOSA that have been introduced to VITA. Now, some of the profiles could be pre-existing, but others have been created and then submitted to VITA and adopted by VITA, where the rest of the industry partners can use these profiles, and system builders can make use of these profiles in the open space through OpenVPX. So as Mark pointed out, we have payload and processing profiles here, and this profile next to it being one that has white space, which is for I/O. And this is what SOSA is attempting to, or is limiting, so that we have a better and more managed interface that provides interoperability amongst the profiles that are tightly constrained or they're well defined. Further, we have switch profiles, and we've discussed some of those, the primary switch profiles that are shown here. In addition to that, Roger was discussing new fiber optic apertures that are shown below in this group of profiles through Beta 67, and this provides us with apertures that support both RF and fiber optic. So as we look at building a system and a system that would be enabled through the work at SOSA, there's a need for infrastructure. So the elements of the infrastructure include network, which is high-speed switching to connect the modules together, payload, which are the modules that do the work, and this would include DSP and processing, timing, which distributes timing in the system, called precision navigation and timing as a module, system management, which is a way to manage the modules amongst the modules and also to pass that information up to a higher level entity above it. And then power systems, a way to provide power in the system implementation across the modules that are present to power them. By way of looking at impacts of trends and the effect upon OpenVPX and SOSA as well, a few things to note. As systems evolve, we look for higher bandwidths between the modules, or actually from the modules, being able to communicate at higher speeds. And two standards that are widely used are Ethernet standards and PCIe standards. PCIe for low latency peripheral interconnect and Ethernet for network infrastructure. Recently, we've seen the development of 100 gigabit Ethernet, which uses 25 gigabit lanes. So we've moved from 10 gigabit to 25 gigabits per lane, where 4 lanes allows us to reach 100 gigabit speeds in Ethernet. And if you look at this chart, you can see the times that the Ethernet standards have taken to develop over time. And between 2010 and 2020, we've had quite a few new introductions by way of the 100 gigabit Ethernet standard, and forward there'll be a standard that addresses 400 gig. On the PCIe front, we're moving from PCIe Gen 2 to PCIe Gen 3, and now PCIe Gen 4. So looking at that trend going to PCIe Gen 4, we move from 8 gigatransfers per second to 16 gigatransfers per second at the interface level. So what implementation challenges does that challenge us with? We have the need for backplanes to operate 2.5 times faster. So this is a large increase, and it challenges the backplane design with a few things. One is the need for signal integrity modeling and simulations. This need continues to increase, where one has to model each trace in the backplane and look that it will perform, and do that through a set of simulations. Also, we need to use new materials. Typically today, we might use a material like Megtron 6 at a 10 gigabit rate or gigabaud, moving to Megtron 7 for the higher rates that are required to implement 100 gig and higher PCIe transfer rates up to 16 gigatransfers per second. Further, we run into a need at the backplane level to improve the connector throughput. And this has been in the works for some time, and now with VPX adopting the Tyco RT3 connector, which is backwards compatible to RT2, where we practically had a 10 gigabit limit with the connector prior to that, and now we have a connector that will support the channel rates that are required for 100 gig. or 25 gigabaud. So as we move on, looking at the infrastructure requirement for network connectivity, largely modules within a SOSA system are connected via Ethernet for the primary network connectivity and control and data plane. And in expansion plane, as Mark discussed, there are several other protocols that can be used, PCIe, Aurora, etc., that can be used between the modules. Because of Ethernet being widely used, there's the need for a primary switch profile that allows both data and control plane in a switch to be represented for infrastructure connectivity. So the profile on the left provides 6 fat pipes at 10 or 40 gig. It provides ground separation between the data plane and the control plane for isolation, and then it provides 7 ultra-thin pipes for 1 and 10 gigabit connectivity between the control nodes within the system. Likewise, there's another profile, the secondary profile, that allows fiber optic to be used at the bottom through the 67.3D aperture, and this gives us a way to augment the capability of the switch with fiber optics. And then for legacy needs, there is a hybrid profile that provides PCIe and 1 and 10 gigabit and also thin 1000 base T. So looking at some other challenges, as the profiles are updated, we see that the old Ethernet 6U or switch profile organized the thin pipes at the top for control plane and the fat pipes at the bottom. And the new profile has been arranged such that the thin pipes are to the bottom of the profile and the fat pipes are at the top. These are some of the things that we have to adopt to as the new profiles are introduced, and manufacturers have to align with this to provide new switching technology aligned to the newer profiles that are emerging. By way of cooling, as performance increases and we use FPGAs, high performance parts, and CPUs, we use multi-core single board computers, etc., this all takes power. And what we've seen is module power for typical conduction-cooled modules ranging, let's say, up to 60 to 75 watts. A limit is hit, and there's a need for a different cooling technique because modules have power demands that exceed 100 watts, could be 130, 150, or higher. These require new cooling techniques, and the new cooling techniques that have been introduced through VITA include airflow through cooling, or AFT, in VITA 48.8, and liquid flow through cooling in VITA 48.4. These techniques, these new standards for cooling, are being adopted, and manufacturers are producing modules that use airflow through cooling capability. So you can see on the bottom right that what a module looks like that has the 48.8 capability made by Annapolis Microsystems, where it provides a set of fins that allow air to be sent through the card and provide a greater heat dissipation capability within the card using AFT. This requires, in the packaging end, new card guide technology and also requires new heat sink designs, so this affects the chassis design itself. We spent some time talking about connectors, both in RF and fiber. This is an example of an ELMA backplane that uses VITA 66.4 connectors. As fiber optics emerge, we're seeing another standard, VITA 66.5, for fiber optic pass-through with an integral transceiver on the payload module, and likewise there's a mating connector that's necessary on the backplane. So we have several new standards, including 67.3, that provides various apertures that can be used for the connectors that are presented in the P2 section, and these can support both RF and fiber And we have a lot of industry participation around this in connector manufacturers and also transceiver manufacturers to produce these transceivers for the board payload manufacturers to use. In looking at power, Roger had mentioned this. SOSA is driving 12-volt, 3.3 aux environment, and this is constraining the number of power rails from the legacy VPX approach. In VITA, this will be a recommendation, but in SOSA, it is a requirement to normalize the power scheme. This provides for better interoperability. Also, we see power modules beginning to use VITA 46.11 to provide intelligence in the power supply so one can communicate with it and control it. So this is just a chart illustrating the power as it exists today with the legacy 5-volt, 3-volt, and 12-volt, and then what would not be used in the proposed implementation for SOSA. So the modules become more simple where the power supply rail is derived primarily from 12 volts and 3.3 aux is also present. As we discussed, system management's also being fleshed out. It's a relatively involved topic, but it leverages existing technology that had been used in PIC-MG and also in NTCA, and this is being further adopted and defined for use within SOSA. So in summary, we have new technology and standards having an impact on OpenVPX profiles, driving new chassis, backplanes, and power systems design. We have backplanes needing to operate at 25 gigabits per second and beyond, and networks will use 100 gigabit in 3U and 6U Ethernet switches, and this is happening as we speak. People are developing these things. PCIe will move from 8 to 16 gigatrans per second. We also are seeing cooling techniques evolve from VITA 48.1 and 2 to include 48.8 air flow through and 48.4 liquid flow through. Power supplies, solutions evolving to 12-volt, 3-volt aux in a two-rail design. The use of fiber optics for higher bandwidth connectivity external to the box and also internal to the box. And then this leads us to reference designs relative to backplanes being produced to prove this out, and this is an area where ELMA is involved in this development to build reference systems to allow us to test the technology. So that brings me to the end of my presentation. Lisa, handing back to you.
Oh, that was great. Thank you, Ken. It's time now for our audience Q&A. Please send questions by using the Ask a Question box. While we wait for your questions, I'll take this opportunity on behalf of TechBriefs Media to thank the sponsors who have made this webinar possible: Atrion, Elma Electronic, Contron America, Meritech, and Pentek. Next to the Ask a Question box is the Resources link, where you may download technical papers from the sponsors as well as PDFs of the speakers' slides. And now let's begin our Q&A with this first question, which goes to Mark. Mark, what are some of the pitfalls or inherent deficiencies, if any, for SOSA? And where would you not consider using SOSA?
Thank you, Lisa. This is a great question because it's something we wrestle with in the working groups all the time. We realize that the space we're working in is these high-performance sensor-based systems, but that what we're doing actually has applications well outside that. And we also are very cognizant that we can't solve all of the world's problems. And so we tend to use an 80% rule, where if we come up with a use case and go, oh, we can't do this because of this particular use case, we try to examine it and say, does that one use case fit within this 80% rule, and we have to constantly balance between the good of that 80% of the market versus what this edge case might require. And so we're trying to take in as many use cases as we can, but we realize that there's going to be examples out there that these technologies simply won't be suitable. Problems where you might have very intense low latency issues or legacy protocols that you need to communicate over and things like that. So we're cognizant of it, and we just want the standard applied where it best makes sense.
Thanks, Mark. Ken, you have the next question. Someone in our audience wants to know, how will interoperability be guaranteed if you mix and match from different manufacturers? And will there be independent certification labs? Is this a golden opportunity for a new generation of small integrators picking from the smorgasbord of available products? Ken?
So this is a great question, and it's one that has been a primary effort within the working group. As part of the standard development, one needs to think about conformance and how you'll conform to the rules that are being developed by the standard, and then how you'll actually test and certify those things. The question is also rooted in why, at this point, we can't really say that anybody's compliant or conformant to SOSA completely, because those conformance rules need to be, or conformance processes need to be developed and be incorporated in the standard and then executed so that one can take their module through the conformance testing. So yes, there is, as part of the standard development, there are tables of conformance items that are being reviewed and included that are still being worked, and then there will be a process to prove your module and an entity that will exist to assist with conformance. So that's coming, and it may be a good opportunity for someone to get involved with as the question was proposed. Also, there will be the need for test suites, and some of those are being developed, as well as test systems that will be used to verify SOSA cards through the process. So one can expect to see that coming as time goes on.
Thank you, Ken. Roger, this question is for you. Given SOSA's emphasis on sensor-based technologies, what is your prediction of how it will affect COTS suppliers from a business standpoint? Roger?
Another great question. First of all, I think the speed with which new specifications, new flowdowns from government requirements will be streamlined by using this SOSA specification. There will be perhaps a quicker arrival at a final statement of work and spec that will satisfy the government and will give vendors like ourselves, COTS vendor, something to get earlier rather than later. Secondly, the fact that there's a tri-service convergence is that these platforms that we're talking about might not only be used, for example, by the Army, but might also be used by the other divisions as well, the Navy and the Air Force, because they are then also more of a standard system architecture than something custom-made. And lastly, what I would say is that one of the things that the government struggles with is trying to get new technology into its systems, and sometimes this in the past, frequently, this required replacing systems. With the upgradability that SOSA promises, these systems can be refreshed technology-wise and therefore perhaps generate more business than otherwise would have happened without the SOSA initiative driving the specification of that particular architecture.
Thank you, Roger. Mark, here's a question for you. Does the prescriptive nature of SOSA inhibit innovation? Interesting question.
Indeed, and indeed, and it's something we hear a lot of, and it's a natural thing for people to be concerned about. Oh, we won't be able to really innovate, but I will argue, and a lot of folks will argue that it will, in the end, enhance innovation rather than inhibit it. Certainly, at the board level, vendors are able to come up with all kinds of new and innovative products that they can offer in their catalog, with new features and things like that. It's the only way that they're going to be constrained is in how they connect those products to other products, perhaps from other vendors, or to legacy products. And even though there might be rules that define how one slot might be connected to another in certain instances, there's almost an infinite combination of ways that those slots can be connected. I'll give you a perfect example. The expansion plane has the ability to have direct connections. In fact, all of the planes, the data plane, control plane, and expansion plane, have the option for either switched connections or direct connections. That right there allows for a tremendous amount of connectivity. So I think that once people start digging in and start thinking through, you'll find that there's plenty of room for innovation within the SOSA constraints.
Very good. Thank you, Mark. And with that, we're at the end of our webinar. I want to thank our speakers for sharing their insight with us today. I also thank our audience for being with us. A survey will pop up on everyone's screen immediately following our program. Please tell us what you thought of our webinar by answering 3 short questions. This webinar will be archived and available for viewing on our website. An email will be sent to everyone who registered for today's program as soon as the archive is ready. Once again, thanks for joining us.